Um, Hi. I wasn't sure if I wanted to start with hi. I always say that, but here's some normal random variable problems. I'm going to do them first by integrating defined probabilities, and then I'm going to use the normal table. So I'll do exactly the same problems once by integrating, and then I'll make a new video by using the normal table. But for now, we'll just look at them. Just as we've done any continuous random variable, there's a probability density function, and then we integrate that probability density function defined probabilities. The thing about the normal is it has it doesn't its probability density function doesn't have a closed form antiderivative, so that's why we use tables to make estimations. Um, and that's why, again, you might use maple, and a lot of times you'll get that there's a function maple spit back ERF. It's just it ERF is a function of e to the negative x squared. The problem is, right, there's no closed form antiderivative for e to the negative x squared, so that's the issue. So a lot of times I'm doing eval f, or I'm asking, maple can give us, again, it in terms of a function, this ERF function, but you have to evaluate to get a numerical approximation. So anyway, let me just go ahead and start. This, the length of a rod, so this is a continuous random variable, length, right? It could be anywhere in an interval. It has approximately a bell-shaped curve. The lengths are have a mean of 75 centimeters, so that should be about the center or the mean of the bell-shaped curve, and a standard deviation of 1 centimeter. Okay. Find the probability that we randomly select a sheet and it's between 74.5 and 75. So that's what we're going to integrate between. So here's the thing. Here's the probability density function for a normal. It's 1 divided by square root of 2 times pi times the standard deviation, which is 1. Okay, so there's 1 over square root of 2 pi times sigma times e to the negative x minus the mean, which is mu. I square that, and I divide that whole thing by 2 times, in this case, sigma squared. And that's my density function, and it's valid for all real numbers. And when I put this in maple, I always check and integrate over all real numbers to make sure it integrates to 1, because it's very easy to make a mistake for this probability density function when you input it. I'm trying to find the probability that that random variable is between 74.5 and 75.8, so I'm going to integrate over that interval. Sorry about that. Okay, so let's actually, I'm just going to copy and paste this, and I'll make sure it is correct. F of x. Let's see. Yay, it looks good. It doesn't look exactly the way I wrote it. It tries to take the square root of 2, put it up top, but it leaves the square root of pi down there, so it's just rewriting it. Let's integrate f of x from x equal negative infinity to infinity to make sure we get 1, because it's very easy to make a mistake when you type that in. So the probability that a rod is between 74.5, so x equals 74.5 to 75.8, and yep, that's the right thing. So it's about 50%, and let me show you a plot, right? You're always going to get, let's just go between, the mean was 75, right? Standard deviation of 1. So let's go from 72, well, let's go 71 to 79, and you'll see the bell curve then. That's the graph of f of x. And you can see that center at 75. Standard deviation of 1, that means about 68% of your data is within 1 standard deviation. So from 75 to 76, there's about 68%. 73 to 77, 95%. 72 to 78, 99, 7%. So most of your area is between 3 standard deviations. And I think that's good for this problem. I'm not going to do, again, I'm not going to use a z-table on this. I mean, you always have integration as a technique for solving for continuous random variable probabilities. So, I mean, a table is a convenience, but you can always go back to first principles. There's got to be a density function, and you just integrate under that density function. Okay, let's hit another one. Here's another normal. Suppose scores on a dexterity test are normal. So x is equal to dexterity scores. Dexterity scores. And x has the distribution of a normal with a mean of 12 and a standard deviation of 3. And what's the probability? Well, that no one will score less than 14. That's a different random variable, but for now let's just figure out the probability somebody gets a score less than 14. Then we'll worry about what's the probability none of 8 people get a score less than 14. But right now we'll just do this. So I don't know if you can hear it, but I'm in Heritage Trail, and this is when the train comes through. Sometimes it gets really loud. So let me put f of x in. 1 divided by square root of 2 times pi times sigma, okay, times exp, the negative x minus mu is 12, divided by 2 times sigma 3 squared. Looks good. Let's integrate. Integrates to 1. Let's find out the probability that somebody gets a score less than 14. So, I mean, we could go 0 to 14. There's not really any area to the left of 0. So how about I do it? 0 to 14. And you'll see earth here. And it's just because I put in an integer, so it's trying to evaluate exactly, but so there it is, 7474. I'm going to call this guy P. Let's do that again. P is my probability of success, where success is scoring less than 14. So I'm going to let y be a new random variable. 8 individuals are selected. What's the probability that none will score less than 14? Number of individuals out of n equal 8 who score less than 14. Scoring less than 14 has probability 0.7474, and n equals 8. So this is a binomial. We're really just finding the probability of no successes in a binomial. So, well, actually, I don't even have to do it as a binomial. What's the probability that none will score less than 14? That means they all score bigger than 14. All score bigger than 14 is 1 minus p raised to the 8th. They all score more than 14. Right? What is the probability that none will make a score? So that means the probability all score more than 14. The probability all they score more than 14 is not very likely. Did that make sense? Or I could do it again as a binomial. Y is the number of people out of 8 who score less than 14. So then I could say what's the probability 2 people do, 3 people do, and just set it up as a binomial. Right? The mass function is p of y is equal to binomial 8 choose y times p to the y times 1 minus p raised to the 8 minus y. And then I could just sum that because it is a discrete random variable now. Y is a discrete number of people, and x was continuous dexterity. It's on a continuous scale. One more, going a little bit backwards, just because I wanted you to see normals. Not only do we find areas, but we want to find you know, if they give us a value and say 95% is greater than this value or that value, can you work with it in different ways? So suppose lifetimes of batteries are normally distributed. So let's let x equal battery life, no, not battery, sorry, bulb lifetimes. X's are normal with a mean of 1,000 hours and a standard deviation of 100 hours. Is this company correct when it says 95% of its bulbs last at least 900? Let's just build this guy's density function first. F of x, 1 divided by square root of 2 times pi times 100 times exp to the negative x minus mu squared divided by 2 times sigma squared. Integrate f of x from x equaled negative infinity to infinity. Okay, nice. Yeah, we know a little bit about this. We can probably answer without, just by thinking about the curve. X equal, let me see, 1,000. So if we go, like, let's go 600 to 1,400. What did I do wrong with my plot? Oh no, I did something stupid. Display. Oh, why? Okay, yeah, I thought that would do it. Okay, so here's my plot, and it wants to know if 95% of light bulbs last at least 900 hours. So 900 hours is just one standard deviation away, sitting right here. So it looks like no, 95% don't. I mean, because there's still area down in here. So is 95% of the area under the curve to the left of 900. Well, actually, I'm being silly, right? I mean, sorry. I mean, my 95 will be about right here. So what was the question again? Maybe I have to go back up here. It's coming. I want to claim that 95% of its light bulbs last at least 900 hours. That actually, that's true. My lower bound here, they all last at least, it looks like a number right here. Let's find that value that they last, 95% last at least that long. So I'm going to do something. I'm going to solve. I'm going to integrate f of x from x equal that lower bound, let's call it m, to infinity equals 0.95. Let's see if Maple will deal with this. Maybe I should have said fsolve. I don't know. And it might take a minute, as you see, but I'm trying to find, yeah, that number there. And most of these are imaginary, right? So there it is. Here's my real one right there. There's my real solution. So yeah, 95% lasts more than, that still bothers me, 835.51. There's only 5% in that tail past there. Well, let's see. Let's integrate f of x from x equal 835.51 to infinity. Should be 95%. Yeah, okay, so yeah, I mean, at least 95% of their bulbs last at least 900 hours. In fact, 95% of its light bulbs last, why do I keep, now I'm, no, 95% of its light bulbs don't last 900 hours. It looks like 95% lasts more than 835 hours. So it's just me reading this question wrong. Please don't be disturbed like this is a hard problem. It's just that I'm confusing myself with what they mean by 900 hours. Yeah, I mean, yeah, 835, 95%. So they can't say that. They can't say that they know that 95% lasts more than 835 hours. So there's going to be some bulbs that, yeah. Okay. So I hope that didn't confuse you too much. I can redo it if you want, or I'll do it again when I do it as a normal table. Okay.